Okay, in this series of lectures, 3 lectures, we're going to talk about curve fitting, the process of curve fitting for data. So curve fitting is one of the most important things we start thinking about when we take data sets and we think about trying to figure out if there's trends in the data, if there are variability that we can model in some way in the data. A lot of data collection is potentially noisy. There are measurement errors. There's also noise in the system itself. But what curve fitting tries to do is pull out key and general trends that might be in your data so that you can have some kind of way to do predictive analytics with the data itself. Okay? So the idea of the data here that we're going to work with is think about very simple curve fitting ideas, and also we'll illustrate them in MATLAB. And the idea is to collect a bunch of data. Let's just think about 2-dimensional data at this point. You might have n data points, x1, y1, x2, y2, all the way to xn, y of n. And typically the idea is you've collected this data and you'd like to see if in fact there's some kind of trend through this data. So in fact, let's talk about the sort of the natural things you might think about right away in doing this data. So let's go to a drawing program here. So I want to go ahead and think about that as being my data set here. Okay? So I might in fact have some set of coordinates, x and y. And each one of these dots represents one of these points. Okay, so for instance, x1, y1 would be this first point down here. This point right here is x2, y2, and so forth. Okay, all the way up through the n points. Now, one of the things about this data set you might see is like, okay, so the first thing you might try to do with something like this is just say, look, this thing looks sort of like just a line, a linear growth. And in fact, one of the things you might think about doing is doing a least square fit. And we'll talk about what that means, or a best fit line through that data point. And what we mean by best fit is going to be really important to start to understand, because what you want is a principled way to talk about how to fit your data. Okay? So let's in fact draw what a line might look like. Who knows? This might be something like a line that we might think looks pretty good in picking out that trend. Perhaps I drew it a little bit too low. And I want to think about what it means to think about that data in the context of that line. Because once I have the equation for this line here, then what I can maybe say is that I have the basic trend of the data, even though there's a lot of variability around it. Okay? So this is the standard way of thinking about data. This is, in some sense, dimensionality reduction down to a simple line like that, right? The idea is to figure out how would I pick the A and the B so that that line is the best fit for the data that I've actually shown you right there, okay? So that's going to be the general concept behind curve fitting. And by the way, you don't have to think about just lines. You could imagine fitting parabolas or any other kind of functions through here. The more complicated the function, it can in fact take a little bit longer, or it can be more computationally to solve for. But simple things like polynomials are actually in fact very easy to do curve fits with. And we'll talk about that. All right, so the biggest thing we got to think about then is the fact that when I plot this line, it actually doesn't go through all the data, right? If you look at this line here, it goes through part of the data. We'll light that a little bit better. So it doesn't, in fact, it doesn't go through any of the points necessarily. And so part of the thing you start understanding is, how am I going to talk about the best fit for this thing? And one of the things you start doing is start understanding some error metrics. And this is going to be really critical for what we think about in terms of developing these analytics for this, is to think about what are the error metrics we want to be thinking about in order for you to say that, in fact, I have the best fit through the data. Okay? Now, the first thing we're going to talk about then is the error from any single point back down to the line. So, for instance, this point right here, there is, in fact, some distance. That's my best rendition here of that. Here, again, I have a point here to the line. And I start thinking about calculating these distances from each point back down to the line, right? So, in some sense, this is my error for that specific point. How far away am I from the line, okay, or from the best line that I've got? So every point would have a distance down to this. And so I want to introduce a couple different error measurements, because there's not necessarily just one way to think about measuring the error. Okay, so let me tell you some of the standards. The first one is the maximum error, and it's denoted by E infinity. Okay? And the idea here is that, in fact, what I'm going to do is say, I'm going to talk about this here not being y, but some approximating function f of x. This is going to be my approximation to the line. So E infinity is going to simply be, I'm going to define my error as the maximum. Let me write it down here. Okay, let's talk about what this formula means. So the E infinity error is the max error. It just looks at the distance of your approximation to the line, and whatever the maximum distance is, that is in fact the error. So if we looked here at all this data, the E infinity error would be basically, this is the point here that is furthest from the line, and my error, when I think about this error, is dominated, at least in this measure, by that point there, and this distance right there. That is the E infinity. And so what I'd like to do is figure out how can I change this line to minimize that error. So in this case, you might lift the line up a little bit to basically try to make that as small as possible. But as you lift this line up, of course, this error gets smaller, but this error here gets bigger. This error to this point gets bigger, and so forth. So the idea is you change the line and the slope, you might find the best A and B so that this thing is minimal. Okay, that's one error definition. It just looks at who is the worst performer and then minimize that. A second one is called the average error. Okay, and the average error, E of 1, and all you do, it's just like it sounds actually, is you look at the average distance, k equals 1 to n, of all these E infinity errors. So you think about, I'm going to take the distance between my approximation to the line, add them all up, divide by the total number of points, and this gives me the average distance to down to the line. So every one of these errors here, from the point to the line, I add them all up, divide by the total number of points, and it gives me the average value of that distance. And so part of what I want to try to do then is, in fact, minimize that. Okay? So those are two definitions. A third one is a root mean square error, often denoted as RMS. And it's very similar to the average error, except now what we do with this, it's called the E2. What we do with this is we take 1 over the number of points, so it's going to be like an average, but not the average of the function itself, but I want to look at the square of the distance, and then square root. So what this does is take the point I'm at, or my approximation to the actual point, and I square that distance. And I add them all up, divide by 1 over n square root. Okay? So now, this is interesting. I'm going to penalize heavily if you're far away from that line. So in other words, if you're this point right there, right, you look at that distance, it's no longer just add that distance here and take the average. Now what I'm saying is take this, square it. So now this is going to become a big number here, becomes a really big number in that penalty. And then I'm going to add up all the squares of those distances and divide by the total number. So I'm going to get an average there. And what I've done in this thing here is allowed myself a way of penalizing points that are far away. In other words, I'm going to try to pick that line so that nobody is that far away from the line. And if they are, I'm going to penalize them heavily because now I am squaring the distance. Notice this is E1 error here, and we can talk more about that later in this course. That doesn't penalize the distance so badly. So even if a point's very far away, could be an outlier for instance, the outlier does not penalize heavily this error. An outlier here penalizes very heavily because you're squaring that distance. Okay? So of all these three techniques, the root mean square error is typically the most commonly used in practice. It's a very nice technique. It again penalizes. It doesn't handle outliers very well, but for most data, this actually works quite well. It tries to get the best fit and that you're not too far away from the line. Okay. The question is now, how are we going to determine the A and the B?